Today we want to get started with the Laplace transform in chapter 9. I'm going to do it kind of in a unique way, I guess, hopefully. I'm going to start from the back side and come at it from the point of view of what you must do first, second, third. So you get the whole picture. It should make more sense. So here is off the web a analysis of kind of a simplified analysis of what we're studying. And it's not, I'm going to put this on my website so you don't have to worry about getting it. It'll be available on the website. But I wanted to go down to a point in it where you have to use certain, like a model of the circuit in order to get your correct response. So this is sort of it's somebody was teaching this, and this was not on the first page of the query that I did. It was down deep. So I wanted to give you a how to look at various components. Okay, so in the time domain, this is what you have right here. But in the S domain, this is what you have right here. So if you write V is equal to R times I, you're in. So you can drop the parenthesis S because this is just saying it's in this. It's in the frequency domain or the S domain. So you can explain it by rooms. I'm in the time room, or I'm in the frequency room, or in the S room, and this is in the S room. This is the rule, okay? So that's the rule for resistors. Now this is the rule for inductors, which you've seen before. E equals L di or Eli. This is Eli, okay? V. Okay, so it's V is equal to S times L times I minus L times I naught. Now this means when you turn the circuit on, I naught is the current at t equals 0, or when you start. Okay, so that's the precondition. Excuse me, yeah, okay, so that's that one. Now this is the other one. Okay, so here's the equivalent circuit for that. Now I want you to see this, because when you look at it, you say, what on earth is this guy saying? Well, he's basically saying this. When you see an inductor in a circuit, what you replace it with is this or this. So on your crib sheet, make a crib sheet. That's my suggestion is to make a crib sheet and write this down. Okay, so when I see an inductor, I do this. Now that's a DC amount. And you notice that the plus is on top and the minus is on the bottom, but the plus is on the bottom of the inductor. So this is S times L, and this is L times I 0. Now, if you want to use a current, which nobody does, but instead of voltage, if you need current, you do this. Okay, so you do this little dookie here, right here. It's S times L. This is your B, A and B, and this would be your current supply. This current supply is I0 over S. Okay, so in other words, if you have a inductor and there's a and there is an I0, you have to use this or you have to use this. All right? If there is no I0, you just use this or you just use this. And everybody get that? That's all of this, that's all this is. All right? What about capacitors? Here they are. So for a capacitor, I is equal to this, but what about voltage? Well, they use here as the voltage. Now here is the I is equal to this. Now the equivalent for a capacitor is this. Okay. So I can write this up here, but really, okay, so let's write this, let's just write this right here. So I equals C dV over dt. So I in the capacitor equal to C, excuse me, S times C times V minus C V0. And here's your companion part of that, okay? A, and then you've got capacitance, 1 over S C. So this is I going in, 1 over S C. And then you've got a current going the other way, which is C times V0. There's your B term. Now, or it's this. I going in is equal to 1 over SC, and then a battery, and there's your V0 over S. Okay, so now, are you thoroughly confused? So when you see a capacitor, that has a pre-voltage on it, what's its I going to be? It's going to be this, right? Well, it's going to, what do you look at it as? In other words, how do you convert um, how do you convert this in the time domain to this in the frequency domain? You convert this to this, or this right here, okay? So this is how you would do it right here. But I don't want you to be so caught up with this circuit, but I want you to see that if you replace a capacitor, you replace it with this thing right here. Okay, this is the resistance of this guy. So if you take and you get V, it's equal to V equals IR. If you leave out the C0, the C times V0, you say V is equal to I over SC, and this is your resistance of this device, and this is what's on. Sorry about that. Okay, so this is this is the resistance of it. This is the resistance of it, and this is what goes along with it. Okay, so this is what you have to add in if there is a preconditioned, pre-stored V0 in your capacitor. This is what goes along with it if there's a pre-current in your inductor. That's basically what you have to follow. So these two are your best friend. Excuse me. This one and this one are your best friends. This one and this one you use if you ever have to use just the I part. But most of the time you don't. Now, that being said, let's go back. And now I've got the Van Valkenburg text, which I copied, and I want you to use for a little bit at least. We're going to look at it. This is my old text from back when. So
I think it's that rotate button that's next to the percentage,
right here.
a little to the left.
Thank you. Thank you. Thank you. It takes me a while this morning to get going, but yeah, thank you. Okay, so this is the text that I showed you the other day, and this is the one that makes sense to me, and it should make sense to you because it is written pretty well, but you have to get down into it for a little ways before you get to the good stuff. You can't. They start out with just a lot of theory, but then you get down into it and you start digging away at it, and you say, okay, now this is a circuit. Simple as it is, it's got a resistor and a capacitor in it. So, in other words, I've got a closed circuit and I've got a resistor, and I can write the closed loop equation for it. Isn't that right? You can write a closed loop equation for that. But now I've got this integral I dt, which is this term right here. What do you replace that with? Replace it with this. 1 over SC plus V0 over S. So when you see this device right here, you replace it with, instead of R, you replace it with 1 over SC and then plus V0 over S, if there is a V0. Does that make sense? That's what you do. Okay, so what you write is you write the equation for, and this is so you can do a general, you can find any voltage or current in any circuit this way. Doesn't matter. You don't have to look for special conditions. You don't have to look for, this is something that okay. So basically what you have to do here is you have to say this. You have to say, okay, so now I've got my V0 here, and I've got this, I've got a resistor up here, and then I've got a capacitor. But instead of just a capacitor, I've got an R, I've got an I going around, and I got a V. But instead of writing 1 over 2 pi FC, I write 1 over SC. Does everybody see that? Instead of 1 over 2 pi FC, I write 1 over SC. If there was if the voltage had been previously on this, I have to go back and I have to re-establish that. What did I just throw away? I just threw away this picture right here. This is the one I just had. And I have to say, okay, now what is it that I have to put in there? V0 over S. Okay. If there is a pre voltage, I have to write it like this. 1 over plus a voltage supply V0 over S. So I have to do it if they give me, if there says it's pre-charged, then you have to do that. If it's not pre-charged, this goes away, all right? So in this case, in this case, there is no pre-charge, okay? So they basically tell you there's no pre-charging to it. Okay, so what do you do? Well, you write the circuit like you normally would. So here, he writes it as Q of 0 plus over S, which is V 0 over S, all right? So what do you do with the rest of the circuit? Well, here's how you write the circuit. Right, so here's my circuit. If I were to write this, if this was an R, I would say I is equal to what? V over R. If this is R1 and this is R2, I would say over R1 plus R2, right? That's how I would do it, okay? Here, this is the R. Or I would say V is equal to I times R1 plus R2. That's the way I would do it. Here, this is my R, it's 1 over SC. But the V does not correlate to just V because it's a constant. V correlates to V over S, this V0 over S. Now you say, where did that come from? Well, that's just the rules, okay? So those of you who took the course already from me, I didn't have time this morning to get a whole bunch of these copied out, but this is from 4450, okay? I don't have enough for everybody, but this is the 4450. Yeah. Right now, it's got around, this recognize, you recognize this? Yep. You remember? Okay, so what does a constant equate to in the S domain? It's the constant over S, right? Does everybody follow that? It's simple, all right? So does everybody follow what we're doing? We're moving from the time domain to the frequency domain so that we can write the, the equation and then use algebra to solve it. It's basically, this is an algebraic way of solving a differential equation, is what it boils down to. All right, so that's what this is about. And you can thank a guy named Heaviside because he came up with all this methodology. And I guess they really criticized the guy in the day because late 1800s, they thought everything had to be theoretically done. He did it practically. And this is a very practical method for finding the current or the voltage in a circuit that's got an L, R, and a C. It's straightforward. Anything, any kind of thing you want to throw at it, there it is. What's new? What's new about this? That initial condition, isn't it? You got to stick that in if it's there. You got to stick it in, and that throws a curveball in the circuit sometimes because you can't combine things as nicely if there is no V0 or no I0. You can combine these real nicely by using the parallel rule. Okay, so if I had a parallel combination of this and this, I can use the parallel rule to combine these. But I can't if there's an initial condition. What do you have to do in that case? Mesh analysis. So you have to choose, or you have to watch the circuit, and you have to be very vigilant if this is there. And if it is, you have to put it in. And then sometimes you're forced, if you have a circuit like this and this is pre-charged, all of a sudden you got a voltage supply down there. How do you find the parallel condition with that? You don't. You have to now use mesh analysis to get this loop and this loop, or you have to use some other, can use Thevenin. You can still use Thevenin. You can use all the rules that you had before. They're still available, but most people use mesh. I'll be blunt. Most people use mesh, okay? That's why I put the mesh analysis in the first test, because I wanted, if you didn't know it or if you didn't remember it, I wanted you to be informed that it's there and it's important. So that's why I put it in. Does everybody see this process? The process is what? You look at what you got, you look very closely if there's an initial condition. If there is, then you have to put the thing in. So if there was, you do. If there's not, you don't. Then you write the equation. So basically you write this, which is exactly what he did. So this is what he did. See that? Right there it is. Okay? Now what do you do with that? From this point on, what do you do? Well, what's the question? You have to ask what's the question. Usually the question is, what is I? Okay? Do you see what he did? I is equal to this times that. It's exactly what he did. It's this, and this is just with variables, okay? And why is it a little I? Because it's a time varying signal. If it's a capital I, if it's a capital I, it's a DC signal. If it's a little I, it's a time varying signal. That's why I use little I. Why do you use capital I here? To signify that it is in the S domain. So again, why do you have capital letters in the time domain? Because it's a DC signal. Why do you have a capital letter in the S domain? Because it's just the way that they do it. So don't be intimidated by all this stuff. It's just tradition. But that's why the little I. It's in the time domain. It's a time varying signal. Therefore, it is that. Now, does everybody see? Now, we've been telling you all along that in this circuit that's what that was. And you just have to accept it. Now you can prove it. Okay? If there's more than one capacitor, if the capacitors are around in various places, that's how you do it. Does that make sense? Because that's exactly how you do it. How do you get from here to here? What rule is that on this sheet? Everybody should have this memorized by now, especially if you've had 4450 from me. What rule is this to here? Rule 2. Okay? Does everybody see that? Rule 2 on this sheet gets from here to here. Does that make sense? That's exactly how you do it. So we go over into the S domain. We mess around with it a little bit. We get it to a point where we've got something that then we can transfer back. This is something that's on the sheet. Boom, splat, done. Okay, so then they do one with a inductor. Oh my goodness. Okay, so what happens with the inductor? Right, in this case, do they have an initial condition? It's 0, so you got to be careful. You got to always watch. See, it's 0. So in that case, what happens? You don't have to worry about. If it's 0, you don't have to worry about it. You do not have to worry about it at all if it's a 0. And that's, where did I put that? Where's that at? It's above this. It's right up here. Sorry about that. If the initial condition is 0, This goes away, and you just have SL. Okay? All right, so that's that. Now you see what we're going to do, right? We're just going to practice circuit after circuit after circuit until you get this down. That's all this is. But this works, and it works across the board. And it's the same thing you learned in 4450, except that what? Now you have to look, in 4450, we give you the differential equation. In this course, you have to come up with a differential equation. That's the difference between the two. This is harder because you have to come up with a differential equation. You have to analyze the circuit, get the differential equation, sort and sift it using Laplace rules, and then you come up with a final answer in time domain. Okay? But it works across the board. And why do we do this? Like I told you, you never, or hardly ever do this in the real world. In the real world, you walk out and you say, you know, but on the other hand, because you've done this and you know how to do this, you basically stand shoulder to shoulder with the electrical engineers. That's one of the main things that they say that, well, I've got. And the chairman of electrical engineering was shocked that you go through this course. He didn't think you did this. I said, oh yeah, we do that. We do that course right here. He was shocked. He didn't think that you did this. You do. Okay? Anyway, and you can use it on your PE test. And once in my life, I actually, like I said, I walked into a situation where I said, how does this thing work? And right here it is. This is the answer to how an L and a C, only two, they just go wow, 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 but they go at a frequency. And you can explain it from this circuit, right? You can build a circuit with a DC supply, and it works like a high frequency device. And that's how a metal melter in a factory works. One of the ways you can melt metal is right here. Anyway, I don't want to bore you, but it didn't happen very often, but when it did, it's like, wow, that's exactly what they're doing. And yeah, you can figure things out occasionally, very rarely, but you can do that. So that's it. We're done. That's the whole step. That's the whole story. Now it's just down to looking at problems and sorting and sifting and seeing how. Now we get down into the part where it gets very interesting, where we say, now partial fraction expansion. How do you, once you've got this thing in the S domain, how do you get it back to the time domain? You got to get it to something that fits on this sheet, okay? And there's three basic types, okay? And he explains some more, and this is what's important about this chapter. He explains some really interesting ones, and this is example number 6, which is basically you'll never do this, okay? But you can if you want to. All right, you can do that. I don't think you ever will, but again, here's the one that you probably will use the most. Or, okay, so this is one. If all roots are simple, okay? In other words, if you have s minus 1, s minus 2, s minus 3, s minus 4, they just break out like this. This is called partial fraction expansion. Partial fraction expansion is something you had in a math course some time back, but that's how this is done. So if all these roots are simple, you just break them apart like that, and that's it. Okay? That's the simple one. Now, the next one is if you have a simple one, but it is squared or cubed or whatever. How do you break that apart? It's the first order, then the square, then the third, then the fourth, up to that. You can't hardly read that, but that's to the nth power. So you go all the way up to the nth power. So you have one without any, one with s minus s1 to the 1, s minus s1 to the 2, s minus s1 to the 3, up to the s minus s1 to the n, whatever it is. So you go up to that level, and you'll never go past 2, okay? I promise you'll never go past 2. But that's how that's done. So again, it's just a simple constant, and what's left? Finding that constant. And we've talked about that in class. That's in 4450, we talk about that a lot. All right, finding that constant. If you have s1 over s minus something squared, it's s minus 1, or it's s minus 1, and then s minus 1 squared, 20 squared, and that's it, okay? But there's an easy way to get this, and I'll show it to you. And they describe it here. They describe it a little differently than it was explained in class. He says take the derivative. You don't have to take the derivative because we'll show you another way to do that. But anyway, the expansion is that, and we'll show you how to find the K1 and the K2, all right? Now, if it is a complex number, in other words, if it is if it's factorable, you can factor it. But if it is a complex factoring, in other words, if you have to expand it like this, s squared plus 2s plus 5, what's the factors of that? Well, it's this and this, all right? These can be done as well, but these require the nice calculator. Or he only does it with the calculator approach. Now, if you do it the other way, I don't care. But I'm going to explain this by the calculator approach, which is either way works, but this is one where the calculator approach is probably the best. Okay. He goes through example after example after example of this. It's kind of theoretical, but on the other hand, he does give some good examples. There are examples from my other my problem sets, I just go through it in 4450. So if you've had 4450, you've got an advantage here because you've already done this before. But if you haven't done it, or if you the 3020, did they go through and do this? And how did they teach this in 3020? Anybody who's taken ENGT 3020, how did they do this there? Anybody that's had that 3020, ENGT 3020? Did they teach this in 3020? Huh? Not much?
Mostly what
And that's it? Well, guess what? In here, you're going to go you're going to go from the circuit to Laplace and then back again. So you're going to, in this circuit, in this course, you're going to analyze the whole thing, all the steps. So again, a lot of examples. We're going to just start working problems, not. Okay, so here is this breaking down of the one where it's this guy right here, and here is the formula for that, and it is 2 times the value of R, whatever that is. So it's 2 times if you take your sheet and write down, when you do the K1 over S minus 1 minus 2 plus 2J, and then plus K star S plus 1 minus 2J, your transformation of this is 2 times K1, which is what he says here, e to the minus this is a e to the minus at cosine of, this is your b, bt plus theta, which is theta is the polar angle of k. So if you get k is equal to a number at an angle, this number is k, and this theta is this number right here. We'll go through that. We'll go through that a lot. But that's what that is, and that's all that is. So if you write that on your sheet, the transposition of this is this. This is the only one that's not covered on that sheet, okay? Please write it on there so you have it, you have access to it. This is the way he writes it. And again, this is old, this is 1950s way of doing things. So here's an example. Okay, so this is how you start out. Now, again, will you ever have a d squared term, or a d squared term? No. You'll have integrals and you'll have derivatives, but you won't have d squared terms. But if you did, this would be the way you do it. But you won't have them. Why? Because you only have a derivative and an integral with a capacitor and an inductor. You will not have d squared terms. But if you did, this would be the way you would do it. Okay, so this is how you would expand, and there's the K1, K2, and then this is one where you have an S and then a complex conjugate number, and this is how you would do that one. This is kind of a, this is a combination one, an explanation. Anyway, here is the kind that you will get. All right?
Hey, Ted,
Yes, sir.
the example you wrote, and you wanted us to write on the sheet, cosine, what did you say?
Cosine, yeah, it's cosine of b times t plus theta. 2 times k1 e to the minus at cosine bt plus theta. Yeah. Now, here is one where there is a precondition. Ah. What is I? Well, you write the equation around the loop. There's a precondition. V0 is minus is 1 volt. So see what you do here? L. Okay, so this is the basic equation for I in this circuit. In other words, you pre-charge, what's going to happen here? You really don't know. If it was just an inductor, you'd say, oh, it's an exponential decay. But now you don't know because you've got what? You've got a capacitor and an inductor and a resistor. You don't know what's going to happen in the circuit because you've never been told exactly how this problem breaks down. You don't know. So here's an example of a problem that for once in your life now you're going to have to crank through this whole thing in order to find out how this circuit works. So basically it is this. L times S times I. So that's this guy over here. That's what? That's the voltage across the inductor plus R times I plus 1 over CS times I sub S plus Q of 0 plus, which is what? Q0 plus is V0 over S, which is exactly what we talked about up here, right there. Everybody follow that? V0 over S. So there we go. That's it. That's what we've got to write. So how do you write that? Well, you say right here, it's I is equal to 1 I times s squared plus 2s plus 2 is the value of that right there. So you've got a minus v0 over s for this term right here. So it's 1 over cs times I plus minus v0 over s. So let's write that out and let's see how that comes up to this term over here. So let's do this. Let's just do this all the way through and follow it all the way through. Not just come to the final conclusion like he does, but follow it all the way through. How do you do that? So here you have an example where it is voltage around the closed loop has to equal 0. So you write it as this: L times S times I. This is the inductor. L times S times I. That's the voltage through here, and there is no I0, plus R times I plus 1 over CS parenthesis I minus V0 over S equals 0. All right, now let's this is I here, Ted. Okay, so let's gather our I's together. So it's I times LS plus R plus 1 over CS. And this is equal to V0 over CS squared. Is that right? Oh, and that's minus 1 over S. Okay. Now let's see what that does, if that equates to this over here. He immediately moves to this formula over here. It's over to all right. So I've got let me go back and look, make sure I've got this right. I think it's, instead of being like this, I think it's supposed to be like that. I over CS, and then, yeah. So it's L times S times I plus R times I plus I over CS minus 1 over S equals 0. So now I've got my I terms, I times LS plus R plus 1 over CS equal to 1 over S. So what do we do to get this correct, or to get this right? All right, so now we go back, and he gets into this term right here by using values for R, and R is 2, L is 1, and C is minus a half. And if he does that, he gets this right here. I haven't cranked through to get that, but that's how you do this. All right. So the 1 over S goes to the right and everything else, and then you get I in terms of whatever, and then crank through it. Let's try. Let's get L here. L is 1. R is 2, and C is a half. So it would be S plus 2 plus 2 over S is equal to 1 over S. Now let's S squared plus 2S plus 2, the whole thing over S. This goes over there, so then I get, yeah, this is what this is. It's exactly what it is. So I get I is equal to 1 over S times S over S squared plus 2, not squared, 2S plus 2. And the S is canceled out, and I have I is equal to 1 over S squared plus 2S plus 2. Now, that's not my final answer. What's my final answer? I've got to convert that back to what? Time domain. So now I do separation of variables. How do you do separation of variables? Well, he does it like this. Okay. Now, in this case, this is fairly straightforward. How is it straightforward? Because you can find this on the sheet. Where is it on the sheet? It's Rule 19. Rule 19 and Rule 20 are your best bets to get an answer. So it is Rule 19. Rule 19 converts it to what? E to the minus t, because it's S plus 1, and there's my A term. A is 1, B is equal to 1, e to the minus t sine of t, and then they put in the, bless them, u of t. Do you have to do that for me? No, but he does. Okay? So be it. Everybody see the answer and how he got it? You see how this works? Kind of. So sometimes you get lucky and you get it on the sheet. Sometimes you don't, and you have to do separation of variables. That's where the hard part. I hate to say that's where the hard part comes in, because the hard part is setting it up. And what does this boil down? What does this really boil down to? These are really long problems. Every one of them is just, they just take a while. Okay. And not only that, and again, it explains an awful lot. It's the general way of finding things, but it just takes time. Now, they do have multi-sim, and you can do this with multi-sim, and you can do this other ways, and this is how they solve the problems. They do it this way. Well, by the way, look at this one. Why did I ask you to do mesh equations? There it is. Okay. So when you see something like this, how are you going to, in a general way, how are you going to find the current through the resistor, or the current through the resistor over here? How are you going to find it? How are you going to do it? You've never been given a general method for finding things until now. Now you've got this big hammer called Laplace, and these specialty rules for loading the Laplace up that I showed you today, and now you can do it. Okay? But you have to do it something like this. Okay? Now, once you get it to this point, how do you find the final answer? Okay, so I'm going to work through this, because this is kind of the thing that, as much as you might not like this, you should be able to do this. You should be able to solve this problem. Okay. Here's this loop right here. So he starts with di. This is this inductor. di1. This is this loop. di1 over dt. That's the current through. Excuse me. That's the voltage through that inductor plus 20, how did he get 20 I1? Well, there's 10 here and there's 10 here, so there's 20 I1. Minus 10 I2, so what he did is he jumped right into the middle, and in order to write this equation, you'd say minus 100 plus 10 I1 plus di1 over dt plus 10 parenthesis I1 minus I2 equals 0. And then you sort and sift. He already did that. Then he converted the if there is no preconditions, if there's no current flowing before I equals 0, what is the equivalent of this? The d is equal to an s, and the 1 over, and the integral, okay, is equal to the 1 over s. That's all you got to do. That's all you got to remember. So instead of writing d, what do you write? S times I. And you're done. Right? So here it's minus 100 plus 20I plus s times I. This is I1 minus 10 I2 is equal to 0. And that's how you get this. That's how you get down to here. Oh, it's 100 over s, excuse me. So from here to here, and I forget that constant over an s, but you got to remember that, okay? And that's how that's done. Okay. Any questions about that? And there's no precondition. If it's a d, it's an s. If it's an integral, it's a 1 over s, and you're done. What about this one? Minus 10 I1 plus s plus 20 I2 equals 0. And he puts parend s. Please don't put parend s. Why do you not want to put parend s in there? Why am I telling you don't put parend s in there? Because it will confuse you. Okay? You think, well, where's that s going? How do I put that s into the formula? You don't have to. Just make it a capital I, or make this a capital I, and you're good to go. So you should say I1, I1, I2, and you're done. And you notice he does that, but he also puts parend s. Please do not put parend s because it will only confuse you. It won't confuse me. Okay? So just leave it as I. So now you get down to here. He wants to find I2. So what's I2? Well, here's your two equations. The I2 is what's on the right for the I2. You follow me? So in the determinant, it's the I1 value, s plus 20, over here, and minus 10. But for the I2, he puts what's on the right. He puts the 100 over s and the 0. And then it's this minus this. It's s plus 20 times 0 minus a minus 10 times 100 over s in your numerator. And then in your denominator, it's this, which is the basic determinant, which is the I1 and the I1 and the I2. Here's your I1 and here's your I2. The determinants are always the same. So if you want to find I1, it's the 100 over s and the 0 over in this column, and then what should be in this column stays in that column. Okay? Does that make sense? The I1 value is the for I1 it's minus 10 and s plus 20, and so this is for I2. I1 is equal to, the right column is as it should be, the left column is the 100 over s and the 0. That's what's in the numerator for the I1. And that's it. So again, and then how do you finish it off? Now this one is a little more difficult because why? Well, it's not really. It's factorable, and he did. And he said it's s times s plus 10 times s plus 30. So that gives you your variables there, and you're on your way. Now, when you have three variables that are like this, it's very simple. All you have to do for your, how do you find this, this, and this? How do you find this term, and this term? Well, you write it like this. You say 1,000 over s times s plus 10 times s plus 30 is equal to a over s plus b over s plus 10 plus c over s plus 30. And then you cross multiply. Equals a times s plus 10 times s plus 30 plus b times s plus 30 plus c times s plus 10 is equal to 1,000. Get rid of your denominator. Now, what do? Let s equal 0. What happens? This term and this term fall out. All that's left is the a term. 0 plus 10, 0 plus 30. So 1,000 is equal to a times 10 times 30. And away you go. A is equal to 3.33. Let s equal minus 10. It's the opposite of what that is. So what happens? The a term falls out, the c term falls out, the b term is all that's left. You have 1,000 is equal to b times minus 10. Minus 10 plus 30 is 20. So what is b? 5. Everybody see that? This one's easy. This one is not bad. And C you can find the same way, and you're done. So sometimes they just fall in your lap. All right? You're done. And then he gives you the same table that we have, except his is a little different, but it's the same thing. Everybody's got their own table. I kid you not, everybody's got their own table. And then you get down to the problems, and I have yet to assign problems. We'll go back to our book, and then we'll use some problems out of it, some problems out of this, and we'll pick and choose, but we'll get some of each of those, and we'll practice them, and we'll practice them, and we'll practice them until we get good at it. And then this isn't bad. I mean, you think it's bad, but it's just a lot of steps. It's not bad. What are you doing in here that you didn't do before? You have to come up with the basic equation. From circuit analysis, you're having to come up with a basic equation, but everything else is the same. We're using Laplace to find the answer. Anybody got any thoughts about it or anything like that? Now, next week, we'll just basically, there's no test next week. Oh, and by the way, I don't think I have to turn in a grade for anybody for, I think I have to turn in a grade for freshmen and maybe sophomores. I don't think I have to turn in a grade for juniors and seniors for midterm grades. If I do, please do not be disappointed. If somebody says you've got to turn it in, if they come at me and say you've got to turn these in, I ignore them. But I do have to do it for freshmen and sophomores, but nobody in here really has to worry about it. But on the other hand, I did not give A's at midterms. Why? Because when I was taking courses, if I thought I had an A at midterm, I always got a B. How's that for a, cocky, confident type of person? I always thought I would, be able to knock the rest of the course out. If I thought I was getting a B, I worked my butt off, and I got quite a few A's because of that. But on the other hand, midterm grades mean nothing. They mean absolutely nothing. You can see where this is going. You're going to have 3 or 4 problems on a test, maybe 5, but they're going to be just like this. So, you'll be able to handle it. After you do enough of them, you'll be able to handle it. But it's based on this sheet. It's based on looking at what you got, what's given, taking it from there. I'll not do anything on a test that we haven't done in class. We'll work through these, we'll work through them until we're good at it, and then we'll take another test. Tests come often in this class, but it will be after the midterm. It'll be a couple weeks, 3 weeks after the midterm, but they come often. And then you'll have a third test, which will continue to work on this stuff a little bit, and we'll do some other things as well. Ability plots, which you've already done, and a little bit of Fourier analysis, and we'll talk a little bit more about the backside of this how you do this stuff. But for the most part, once you've conquered this hurdle, there's not that much more that you're going to get thrown at you that you in the circuits world, this is about the last part. So now you can say, I can do about any circuit anyway, and nobody's going to throw me. When you get into circuits with semiconductors in them, different story. But again, that's electronics. This is circuits without semiconductors in it, for the most part. Any questions? I'm going to cut a little short today, and I'll get you an assignment, but it's not going to be until